All right, so let's start. Um, Today's lecture number 9. The class is 01205216, sections 450. And today is Tuesday, the 6th day of February 2024. And there's a Kaset Fair going on at the university today. So this is an online class, WebEx, and I would like to thank you everybody to participate and to come in and don't miss out. And time is 10:30 in the morning until 12 and 1:30, 1.5 hours. So today we're gonna start a new topic which is called systems. All right. Actually, this class is signals and systems. So there are two two topics, two issues that we need to study. First is signals, which we did. We talked about signals a lot previously in the first 8 lectures, and from this lecture, we're gonna start talking about systems, the second part. Now, a system is a collection of components put together. We put together these components so that it perform a certain task. What it does is that it's gonna take an input. It's gonna take a signal, which we call an input, and the system will process the the input signal, and once it's done processing, it will give out another signal y, which we call an output signal. Now, when when we do this, we call that the system's excited with the input signal, and it will respond to this excitation with the output signal. So xt is the input signal, and xyt is the output signal. So the system will take this input signal as its excitation, and then it will give the output signal as its response. So the output signal is called the response, of the system to the excitation by excitation we mean the input signal. So it takes the input signal that we give it and process the input signal, and it will give the output signal. So the output signal is kind of like a mapping from the input signal to some other signal, which is called the output signal. Now, when that happens, we use suppose we call the system as t. So we're gonna use this notation to mean that the system t takes on the input signal x of t, process the input signal, and map it to the output signal y. So y is a result from the system with the input signal x. Okay, so t transforms x into y. That's what this one means, right? Now, example. Suppose we have this RL circuit, sorry, and we call this circuit system T1, and we take V, okay, V, which is the voltage here, as the input signal to this circuit T1, and we take the voltage across the inductor VL as the output of the system. So if we change V, if we give it a certain signal V, and we use the oscilloscope to measure the output the voltage across the inductor VL. We're going to see that VL, the shape or the characteristics of VL will change according to VT. All right. And now what the question is, what is the relationship between the output signal and the input signal of this circuit? Now we can use circuit theory to write down the KVL equation of this circuit as L di by dt, which is the voltage VL. Okay, we know that the voltage across an inductor is the inductance multiplied by the derivative of the current through the inductor with respect to time. So this is VL, and the voltage across the resistor is according to Ohm's law, so IR, and the voltage VR. This is VR, right? This is VR. If we add VR and VL together, the result would be V. So we add this together, the result would be V. Now, but we need to write down I here, okay, as the output VL, because we want to have a relationship between the input and output, right? So we can plug in this as VL, right, and I as the integral. Okay, so these two equations will define this system. And if we know if we know this function, we can solve the differential equations to find VL. First, we solve the top differential equation, right? And this equation will give us the current IT. Once we know IT, we take the derivative of IT with respect to t and multiply it by the inductance, and the result would be the output signal that we're looking for, which is the voltage across VL. So this is an example of a system defined by this circuit. Okay, or another system called T2 may be defined as this one. So what T2 takes on the input signal xt, and what it does is that it's gonna take a square of x, okay, and then the output will be the product of x by itself, which is x squared t. All right, so for example, if for example, e.g. if x of t is tut, then the output from this system would be t squared ut. Okay, so this is what it does. This is what T2 does. Now, as for T3, what it does is that it's instead of it's gonna integrate the signal x from minus infinity. This should be minus, from minus infinity to t. It will find the area under x up to time t. So for example, if the input signal to this system is delta, then we know that integral of delta is u, right? So the output to delta would be u. Or if the input signal is u, okay, then the output from this system would be tut, etc. Right? Or another system called T4 takes on the input signal and take the derivative of the input signal with respect to time. For example, if the input is t ut, then the output is ut. Alright, it takes the derivative of the input. But if the input signal is ut, then the output signal would be delta, because derivative of u is delta. Alright. Or we may define a system by some differential equation. In this example, the differential equation takes the second derivative of the output plus the first derivative of the output plus minus 5 times the output, and the result here has to be equal to the first derivative the input minus 2 times the input. So this is how the fifth system is defined. So we can see that we could define, there's a lot of ways to define a system. All right, we may describe it as a differential equation. We may describe it as a direct substitution like this one. Okay, so at least two ways to describe a system. Now we are what we are going to do is we're going to be focusing entirely in this course on linear systems. So what exactly are linear systems? Linear systems are systems that if 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 the input is a linear combination of two other signals, then the output would have to be the same linear combination of the output from each of the respective signals. So mathematically, if we let x1 and x2 be any signals, then the system T would be called linear if the output from the linear combination between x1 and x2 is equal to the same linear combination of the output from x1 and the output from x2. That's it. Okay, it's like we can take T inside the parentheses. We could take T inside to the parentheses. If you can do that, then the system will be called linear. Now, it is useful to know that a necessary condition, you know what a necessary condition is? A necessary condition has to be satisfied whenever something is true. So a necessary condition for a system to be linear is that the output signal must be 0 whenever the input signal is 0. So the equation, the necessary condition for a system to be linear is this equation. If we give a linear system, if we give 0 signal to the linear system, a linear system has the output 0 signal out. Okay, nothing else. The response to a 0 input signal has to be 0. Now, what I mean by 0 doesn't mean that it is 0 at any particular time. It means that the signal is 0 everywhere. That's what 0 means. The input signal is 0 everywhere. It means that no input signals. Just that. If there are no input signals, then there would be no output signals. That's what it means. Okay, for a system to be linear. Now, an example, the first example, a system is defined as y equal to kx. Is it linear? Is this system linear? Let's do it. So to prove that it is linear, we have to prove this equation, whether it is true, right? If it is a linear system, then this equation has to be true. So suppose x1 and x2 are any signal. Oh, sorry. Are any signals, and T of x1 is equal to so T of x1 is equal to k of x1, right? By the definition in the problem. Okay, we plug in x1 to x. Instead of x, we use x1. So the output to x1 has to be k multiplied by x1, and t of x2 is equal to kx2. Same reason. Therefore, t of a t of a1 x1 plus a2 x2, okay, by the definition is k of a1 x1, because the problem states that whatever the input is, we multiplied by k, the result will be the output. Okay, plus a2 x2, right? And this is equal to a1 kx1 บวก a2 k plus a2 kx2, but a1 kx1, I'm sorry, but kx1 is t of x1 and kx2 is t of x2, so this is equal to a1 t of x1 plus a2 t of x2. Don't have enough space. Put them closer together so that we have enough space to write down. So a2 t of x2, right? And because x2 and because x1 and x2 are arbitrary, so we have shown that t of the linear combination between x1 and x2 is equal to the same linear combination between the output from x1 and the output from x2. Hence, this system is linear. Okay, because this one is true, this equation is true for any arbitrary x1 and x2, so it follows that this system is linear. Okay, now another example is this. Now we're going to show that this system is not linear. So to show that system is not linear, all right, we may give a counter example to show that there exists a situation where this equation is not true. But actually, in this case, it would be easier to prove that this one is not true. Okay, it would be easier to prove that this one is not true because this is a necessary condition, right? It has to be true. So if this equation is not true, then the system would not be linear. So in this case, it's easier to prove that this one is not true. Now, so let the input to the system be 0 everywhere for all t. Then the output to 0, according to the definition of the system from the problem, would have to be k1 times 0 plus k2, right? And that would be k2. So this system would be linear if k2 is 0. So this system will be linear if and only if k2 is 0. So that basically that means that, for example, the system t of x t equal to 5xt plus 3 is not linear, because in this case this is k2, right? K2 is not 0, so it is not linear. But t of xt equal to 4xt is linear. Okay, in this case, k2 is 0 now, and we have only k1. It doesn't matter if it is negative or not. Okay, it doesn't matter. This is a1. Okay. Another system is defined by the output is the derivative of the input, right? So we're gonna show that this system is linear. To show that a system is linear, we have to show for any input signal. Okay, we cannot give a counter example to show that the system is linear. To show a system is linear is to show it is true for every signal, for every input signal. So we're gonna first let x of t be any signal. All right, then t of x1 x2 be any signals. Then t of a1 x1 plus a2 x2 by the problem. All right, by the problem, this is equal to d by dt of a1 x1 plus a2 x2. Now we learn from calculus that we can take the derivative inside the parentheses, right? So this is going to be a1 d by dt x1 plus a2 d by dt x2, but d by dt is the output, right? So it is a1 t of x1 plus a2 t of x2. And now we have shown that this equation is true for any signals. So that means that the system is linear. The system is linear. Okay, because this equation is true for any signal x1 and x2. All right. Now let's do another example. Now the last example, it was differentiation, right? But in this example, it is integration. So again, we're gonna have to start with let x1 and x2 be any arbitrary signal, any signals. Then okay, same old process again. T of ax1 plus a2 of x2. So I'm gonna copy it to here to save time, right? By the definition of the system, in this example, it is an integral from minus infinity to t, and then we have to plug in t as tau, right? T as tau. So x tau would be the x is the input, right? But input is this guy, so we have to copy it here. A1 x changing from t to tau plus a2 x2 changing from t to tau, and then d tau, right? And now, because we know that integration could be taken inside of the parentheses, so this is going to be a1 integrating from minus infinity to t x1 tau plus a2 integrating from minus infinity to t, the same t, x2 tau. Now what does it mean by this integral? Okay, it is exactly this one, right? So this is going to be the output from the system to the input x1. So this is going to be x1 t x1 t plus a2 t x2 t. Now so at this point we have shown that this guy is equal to here according to our definition of the linearity. Then the system is linear because we have shown that this equation is true for any signal, right? Okay. I would like to uh, to 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 emphasize on this. You have to state explicitly that x1 and x2 be any signal. If you want to prove that a system is linear, then you have to state explicitly that x1 and x2 be any arbitrary signal. If you don't do this, then your proof would be flawed, because this equation has to be true for any x1 and x2. It cannot be true for some particular x1 and x2. There are no exceptions. So you'd have to start with this sentence, okay, and show that this is true. All right. Now another example defined by this equation. Now I'm going to show that this system is not linear. Okay, but here in this case we cannot use t0 equal to 0 anymore. In this case we cannot use this. So what we're going to do is gonna give a counter example. Again, to show that something is not true, we only give a counter example. But to show that something is true, we need to show that it is true for everything, okay, for an arbitrary signal. So now we're going to show that it is not linear, so we're going to give a counter example. So counter example, to show this is not linear, we can give a counter example. Okay, so to this end, to this regard, we let x of t be equal to x of 1 t be equal to 5, and x of 2t be equal to minus 5. Okay, then if we add these two together, x1 x2, so then t of x1 is going to be 5 squared, and that is 25, and t of x2 is the same, which is minus 5 squared, and it is 25. But if we add the input together, x1 plus x2, we're going to find that it is equal to t of 5 plus minus 5, and that is t of 0. But t of 0 is 0 squared, right? Is 0 squared, which is 0. And we see exactly, it is obvious that this is not equal to t of x1 plus t of x2. I'm using a1 and a2 equal to 1, okay, in this case. So in this case, I let a1 equal to a2 equal to 1. So now there is a case where this equation is not true. So this means that this system is not linear. Oh, not linear, because there is a case where the linearity condition is not satisfied. Another one here, we're going to show that this system is not linear. Again, to show that it is not linear, okay, we can again give a counter example to show that this particular example, the equation is not true. Again, we let x1 equal to 5 and x2 equal to minus 5. Then you can repeat the same process. T of x1, I'm using a1 equal to a2 equal to 1 plus a2 plus x2 is t of 0, and that is 0, right? But t of x1 equal to t of 5, and that is absolute 5, which is 5, and t of x2 equal to t of minus 5, and that is absolute minus 5, which is 5 again. So we see that if we add them, t x1 plus t of x2 is 10. And you see that these two are not equal. They're not the same. They're not equal. There is a situation where these two are not the same. So we conclude that this system is not linear. Since there is a case, there is a situation where t of a1 x1 plus a2 x2 is not equal to a1 t of x1 plus a2 t of x2. So we can conclude that this system is not linear. Okay, so right here, to show that to show that a system is linear, we have to show that it is true for any signal. But to show that a system is not linear, you can give a counter example that this equation is not true for this particular signal. All right. Now let's look at this example. Now I'm not gonna give you any details to this. Well, actually, yeah. Like, we're gonna prove that this system is linear. Okay, so we're gonna let x1 and x2. Now, to show that something is linear, we're gonna always start with this sentence: let x1 and x2 be any arbitrary signals. Then, you see, from this equation, the system takes the input signal to here, and if y is the output, then y has to satisfy this equation. Then dy1 then suppose that y1 and y2 are the outputs signals from x1 and x2 respectively. So we have dy1 plus k1 y1 is has to be equal to k2 x1, right? Because y1 has been assumed that has been assumed to be the output from x1, right? And as for y2, it is the same because y2 is assumed to be the output from x2, so it has to satisfy this equation. Now, we can, if we add these two together, okay, we add these two together, the result would be d by dt, right? y1, alpha y1, a1, well, yeah, a1 y1t plus a2 y2t plus k1 a1 y1t plus a2 y2t is equal to a1, sorry, is equal to k2 a1 x1 plus k2 a2 x2. Okay, and we can rearrange it as k2 a1 x1 plus a2 x2. So this is the input, right? And this is the output. So from here, from this equation, we can see that the output from this input is exactly equal to this, right? And so, but y1 and y2 are the responses from x1 and x2 respectively, right? Sorry. Hello. Sorry. And so we can say that a1 y1 plus a2 y2 is the output from the system when the input is a1 x1 plus a2 x2, right? But since x1 and x2 are arbitrary, so the system is linear. Since x1 and x2 are arbitrary, this system is linear. All right. So again, now, so this is the concept of linearity, linear systems. Okay, now let's. If you have any questions, you can raise your hands or you can ask me. You should not raise your hands because when I teach, I'm looking at the screen. I'm looking at the iPad. I can't see the screen. So if you raise your hands, I can't see your hands. You might have to. You might have to
อาจารย์ครับ
yeah.
ไอ arbitrary นี่คือต้องกำหนดมาครับ
No,
หรือว่า
arbitrary
ผมต้อง
means
รู้เลยครับ
anything. Arbitrary means you can plug in x1 and x2 as any signals. You know what the word arbitrary means is arbitrary. Arbitrary means anything.
เข้าใจครับ
All right.
ครับ
Okay. I did not specify x1 and x2 to be anything, right? I'm just saying x1 and x2 to show that the system is linear. I cannot plug in x1 and x2 as any particular signal, but to show that system is not linear, I can plug in because for a system to be linear, it has to satisfy any input signals. Okay, but if there is at least just one input that the condition is not satisfied, then the system is not called linear anymore. Okay?
อาจารย์ครับ
Yeah.
แล้วมันต้องเงื่อนไขอะไรครับถึงจะใช้ counter example ได้อะ
Oh, okay. If you want to show that a system is linear, let me write it down. If you want to show that a system is linear, okay, you want to show that this is true, then you need to show that t of a1 x1 plus a2 x2 is equal to a1 t of x1 plus a2 t of x2. You have to show that this equation is true for any arbitrary 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 x1 and x2. Okay, to show that it is linear, then this equation has to be true for any input signals. But if you want to show you want to show that a system is not linear, then you may give a counterexample. Then you may give a particular case of x1 and x2, right? You may give a particular case of x1 and x2 for which this equation, I'm gonna copy it, is not true. You may plug in x1 and x2. You may plug in x1 and x2 as anything and show that this is not true. If it's not true for at least one pair of x1 and x2, then the system is not linear. Is that clear?
เคลียร์ครับเคลียร์ครับ
All right. Okay. So that's what I did.
มันก็คือแบบมันก็คือสูตรเดียวกันนะแค่แบบว่าถ้าจะเช็คลีเนียก็คือมันต้องถูกนะถ้าไม่ถ้าแบบว่าถ้าไม่ใช่ลีเนียก็คือไม่ถูกแค่นั้น
If it's linear, then the equation has to be true for any for all input signal. If it's linear, this equation has to be true for all input signals. But if it's not linear, then you can give a counterexample to show that this is not true. Okay, you got that right? That right. So this is the set of all signals in the universe, right? To show that it is linear, then this equation has to be true for every member of the set. But if there is at least one member of the set that makes this equation not true, then it is not linear anymore. Okay, right? So you may give a counterexample to show that this equation is not true, and if such a counterexample exists, then the system is not linear. You cannot call it a linear system anymore. To be able to call a linear system, this equation has to be true for every input signal. Okay? Now, another concept which is equally important is the concept of time invariant systems. Basically, what a time invariant system means is that For a system to be called time invariant, its characteristics have to be the same regardless of time. Okay, for example, if you measure some, if you give an input to the system at time 0 and you measure the output and you write down the output, right? And then 10 years later, you give the same input signal to the same system and you measure the output and you compare the outputs from 10 years ago to the output from the present. If they're exactly the same, if they look exactly the same, then the system is called time invariant. The system itself doesn't change with time. The system itself is invariant to time. It doesn't get old. It doesn't deteriorate. It doesn't degenerate. It doesn't get better. It doesn't get worse. The system's exactly the same. That's what it means by time invariant systems. Okay? So, for example, if you have a system, okay, if you have a system and this is the input path and this is the output path, right? And you give the system this signal. If you give the system this signal, which is the unit step signal, okay, if you give the unit step signal to the system, and you measure the output using the scope, and you find that the output is this. Okay, you give the input here and you measure the output here. Now, sometime later, instead of plugging in the unit step at time 0, you plug in the unit step at time sometime later. Oh, sorry. You shift the unit steps, so let's say time t0 later. Alright, you shift it to times t0 and you give this signal to the same system. Now, for the system to be time invariant, the resulting signal has to be exactly the same. Instead of occurring at time t0, it has to be occurring at time t. Instead of occurring at time 0, it has to be occurring at time t0. Here. So here, see, these two output signals are exactly the same for the same input signal. Okay, these two input signals are the same, right? Just that the bottom signal is applied some time later. So the output has to be occurring at some time later, right? But it has to retain all the characteristics, okay, because the inputs are the same. So this is called, when this happens for every input signal, the system would be called time invariant. Okay? The system doesn't change with time. It gives whatever it has, the unit step input, it gives the unit ramp output, right? So whenever it sees the unit step input, it will give out the unit ramp output. Okay, so this is what it means by time invariant. Now, mathematically speaking, to be concise, the system T is called time invariant if for any real number t0, if y is the output from x, then the output from x shifted by t0 would have to be y shifted by t0 as well. Okay, so with regard to this equation, with regard to this condition, this is x. of t, and this is y of t. Suppose we have y here. Y is a result from x, right? Then if you shift x, this is x of t minus t0. You shift x, right? And you give this signal to the system. Okay? The output has to be the same, except that it has to be shifted to the same value. And this is y, t minus t0. Okay, so this is what this equation means. This is what this condition means. All right? Any question, please? Is there any question? No? Okay. Now let's look at an example. Again, to show that a system is time invariant, to show that a particular system is time invariant, I'm going to call it Ti, and I'm going to call this equation 1, condition 1, condition star. I'm going to call this condition star. All right. Now, to show that a system is time invariant, we have to show that condition star is true for any arbitrary, yeah, x and t0. Okay, but to show otherwise, we can give an example, a counter example of xt such that condition star is not true. Same as linearity, right? Same as linearity. To show that something is true, then it has to be true for every any input, right? But but if there is some, at least one input that doesn't satisfy the condition star, then the system is not time invariant. Okay. Now, in this example, I'm not going to show that.
อาจารย์ครับ
Yeah.
ผมย้อนไปนานครับ
Okay.
condition อะไรนะครับ
Oh,
condition ด้านหลังคืออะไร
here. This condition.
อ๋อโอเคครับ
This condition.
โอเคครับผม
All right. Now, in this example, I'm going to show that the system defined by this equation is not time invariant. So, what do we do? The trick is to write down two paths. This diagram, we're going to give a counter example showing we will give a counter example where we're gonna let x equal to ut. Again, we are showing that it is not true, so we can give a counter example. But if you want to show that it is true, then you cannot give a counter example. I'm stressing that. All right. So we're gonna give a counter example to show that it is not time invariant. So I'm gonna let x equal to u. So I'm gonna give u to the system, right? Now, uh, uh, the trick is to draw this diagram. Uh, so this is system T. Okay, this is system T. We put the input to the system, right? First, we put the input to the system, and look what the system does to the input. So what it does to the input here is it's gonna time reverse the input, right? So whatever we put into the system, it will time reverse it. Okay, we time reverse it, and then we delay it 1 second. Okay, we delay it 1 second. So what do? We learn from chapter 1 that to delay a signal, right, we have to plug in t minus 1 to t, right? So because this here is u of minus t, so we plug in t minus 1 instead of t, we're gonna get u of 1 minus t. But if we delay u first, we're gonna get u of t minus 1, right? And then we put it to the system, we time reverse it, we're gonna get u of minus 1 minus t. And you see that these two are not the same. So that means that the condition star falls apart in this case. So that we can conclude that this system here is not time invariant. Again, let me clarify it. In the first path, in the top path, right? What I did was, um, uh, I put, yeah, this is y of t minus 1, okay, and this is t of x of t minus 1. This is x of t minus 1. This is yt. Now, for this system to be time invariant, these two quantities, these two signals have to be the same, right? This is the output if we put the signal at time 1. Okay, if we delay the signal by 1 second, this is going to be the output. But this is the output from time 0 and delay it to time 1. Now, for the system to be time invariant, these two has to be the same, right? So have to be the same if the system is a time invariant. So to show that these two are the same, we perform this trick. We perform this diagram, right? First, we put the signal u to the system. We record it, and then we delay whatever we have recorded. Okay, we got this one out. And the second path is we delay the input. 1 second, okay, to get this one, and we put this to the system, right? So what the system does is it's going to time reverse the input. So we all know that to time reverse the signal, we have to change the sign of t to minus t, right? To minus t. So you see the results from these two processes are not the same. So that means that the system here is not time invariant. Again, here, this is what comes out of this guy. Okay, this is what comes out of the system. If we put the unit step to the system, this is what comes out. All right, and this is the delay. This is the delay of this one to the right 1 second later. And as opposed to we put this input, the delayed input to the system, and this is what comes out. Now for the system to be time invariant, these two have to be the same, but they're not. This is the signal from the first path. This guy is this one, okay, and the other one here is this one, and they're not the same, so the system is not time invariant. So let me write it down for you. uh, it might be easier somewhat less confusing method to show the time invariant property of a system is to consider the diagram below. Okay, the diagram goes like this. We have an input x, right? And the path breaks split into two. In the in the upper path, we put x to the system to investigate. This is a system to investigate, right? And then the output from the system will be delayed by t0. Now we record whatever comes out. Okay, this is going to be y of t minus t0 that comes out. Now the lower path, instead of putting it to the system first, we delay it first. Now we delay it first, and then we then put it to the system to investigate the same system. And what comes out of the lower path, let me copy it. Now what comes out of the lower path, in the lower path, oops, would be t of x t minus t0. This is x of t minus t0. Now for the system to be time invariant, this has to be the same. This is A and this is B, right? For the system to be time invariant, A has to be the same as B for any xt and time 0 t0. Now for the system to not be time invariant, okay, there must exist a signal xt or t0 such that A is not equal to B. Okay. In the previous example, I was demonstrating that the system was not time invariant. So what I did was I gave a counter example, x of t equal to u and t0 equal to 1. And I showed that with x equal to u and t0 equal to 1, A and B were not equal, like we have seen earlier. Now, but if we wanted to show that this system was time invariant, then we'd have to show that these two are equal for all the input and the delay t0. Okay, which we will do in a moment. Any question, please? You can ask anything. Is there anything that it is not clear? Okay, great. So let's look at this equation. I'm sorry. Let's look at this system. Again, we want, in this case, let's draw the diagram. I'm gonna copy this. Sorry, uh, to save time. It takes some time to draw it, so I'm just gonna copy it. So same diagram, right? Now I'm gonna show. I'm suspecting. I'm suspecting that system is time invariant. So I'm gonna show that it is actually time invariant. So I have an arbitrary x. I'm not specifying x to be anything, right? I just write down x. And when x passes this system, what the system does is that it's going to multiply x with k. So what comes out of the system is going to be k of xt, right? And then we pass k of xt to something here which will delay x k of xt by t0. So what comes out from the delay would be k, oops, sorry, would be k, we plug in t as t minus t0. Okay, now that is path A. Now let's look at the lower path. In the lower path, we are delaying x first by t0. So what comes out of the lower path would be x of t minus t0. And then we pass this signal to our system here. Now let's look at our system here. What it does is that it's going to multiply the input, which is here now, to k. It's going to multiply k to the input. So what comes out will be k times xt minus t0. And you see that these two paths give us the same signal, right? Regardless of the input, right? I'm not specifying x to be anything. I'm just writing down x. I'm not specifying t0 to be anything. I'm just writing down t0. And yet, these two are the same. So we can conclude that the system here is time invariant. Okay? Since A is equal to B for any xt and constant t0, it follows that this system is time invariant. Okay, now let's look at another example. I'm gonna copy it again. Okay, this way we can go faster. Now the system in this example is whatever we have for the input, it will output as a sine of that input. Sine of that input. So y is sine of x. Now, in the upper path, we plug in x. I'm suspecting that this system is time invariant. So I'm not giving x as anything, right? I'm just plugging in x and then plug it to the system. So what the system does is that it's gonna output sine of x. So let's write down sine of x here. And then we delay this signal by t0. So we know from chapter 1 that to delay is to put t equal to t0. I'm sorry, t replacing t with t minus t0. So I have sine of x t minus t0. Now let's look at the lower path. We delay x here first. So we got this one, right? And then we put this to the system. So what the system does is that it's gonna throw this into sine. So I'm gonna have sine of x t minus t0. Again, you see these two paths generate the same signal regardless of the values of the signal x and t0. So we can conclude that the system in this example is time invariant. Okay. You following? The concept of time invariant is more tricky than the concept of the linearity. Linearity is more straightforward than time invariance. So, yeah. Now let's look at another one. I also suspect that the another one, the system in the next example is time invariant. So I'm just gonna copy this over to here to save time. Now but only these things change. In the first path, in the upper path, I put x to the system. So what the system does is that it's going to take a derivative of x with respect to time. So what we have here is d of x by dt. I'm going to show that this system is time invariant, so I'm not going to specify x as anything. Okay, and then we delay by t0. So whatever we have for t, we have to plug in t minus t0 here. As for the lower path, we have this one, right? And then we take the derivative because the system what the system does is it takes the derivative, right? So it has to be d by dt, right? X of t minus t0. Okay, so you see that the a and b are the same regardless of x and t0. So the system here is time invariant again. Now, a more interesting case would be the next one. In the next one, I'm suspecting that the system is not time invariant. So let's show that it is not time invariant indeed. Okay, so the upper path, we put x to the system. So what it does is that it's gonna take the first derivative of x, right, and it will multiply by t. So I'm gonna have t here. Okay, and then I delay this one by t0. So every time, everywhere I see t, I plug it in as t minus t0. So what I have here would have to be t minus t0 d by dt x of t minus t0. So this is what it does, right? Delayed by t0 means that everywhere you see t, you replace it with t minus t0. So we have t, we see t twice here and there. So in the first place, we replace it with t minus t0. In the second place, we replace it with t minus t0 again as well. Now in the lower path, we delay the input by t0 we have here. And then what the system does is that whatever the input is, it multiplied by t. So we're going to have this here. Just multiply the input and then take the derivative, right? The output is the product of t and its derivative of the input, but the input is this guy, right? Take the first derivative and then multiply by t. And you see now in this case a is not equal to b. Okay, a is not equal to b as long as t0 is not 0, right? We see that when t0 is not 0, a is not equal to b, right? So there is a particular case where a is not equal to b, that is t is not equal to 0. So this is not time invariant. This system is not time invariant. Okay, this system is not time invariant. All right. Oh, it's a lot of examples. Any question, guys? I hope you all.
Sorry.
Yes.
Can you explain about B path again? That why t is not t minus t0?
Yeah. Look at this equation. Look at this equation. So what it does is that what the system does is multiplying t to the derivative of the input. Okay, do we agree on this one? This equation means that whatever the system does is that it will take the derivative of the input and then multiply the result by t. Now look at this one. This is exactly the same system, right? So what this is the input, right? So it will take the derivative of the input, right? And then multiply by t. See? This is the derivative of the input, right? And then multiply by t. You clear? You see?
Okay, I see.
Okay, it is not multiplying by t minus c0. It multiplies by t. But in the upper path, this is not the system. No, this is just delay. Whatever the signal here is, it will be delayed by t0. So we know that to delay by t0, we have to look at wherever t is, and when we plug in t as t minus t0, right? So there are two t's here, so we plug them all like this. And you see that these two are not the same. So the system is not time invariant. You got that?
Okay, I got that. Thank you.
Okay, sure. Thank you. Good. Now, I'm not gonna do this again. This is the same. So, well, yeah. Let's do it. Let's do it. The next one I suspect it to be time invariant, so I'm just gonna copy this format. Save time. I'm gonna tell you the trick to determine whether it is time invariant or not. The trick is this. If I see time, if I see the variable here, t, that appears outside of x, the system will usually be time invariant. Time will usually not be time invariant. If I see variable time here, system is usually not time invariant. But if I don't see it, if time doesn't go outside of the parentheses, then the system is usually time invariant. And here, t is not going outside, right? So I suspect it to be time invariant. So let's look at this. I'm checking it now. I'm not defining x to be anything, right? I'm just putting x as anything. So once I put x to the system, what the system does is that it's gonna integrate it up to time t, x of tau d tau, right? And then it will delay by t0. So now to delay by t0, you have to look at where the t is. Now there is only t that is here, so I'm just gonna plug it as t minus t0. That's it. Okay, now let's look at the lower path. I have here, okay, I delay it first by t0, and then I put it into the system. Oops, I put it to the system. So what the system does is that it's gonna integrate this, okay, up to time t. Now let's do it. But now I have to plug in whatever I have. This I have to plug in, change it to tau, right? So I have tau minus t0 d tau. Now the last step is to show that these two are actually the same. Okay, these two are the same. Can you do that? Okay, let's look at this. I let u equal to tau minus t0, then d tau is du, right? So the last integral that I have would have to be integrating Now, if tau is minus infinity, u has to be minus infinity as well. So minus infinity. Whereas if tau is t, then you'd have to be t minus t0. So I have t minus t0. I'm just changing variables here. And then x is u, right? Because tau minus t0 is u. Okay? And d tau is du. But u is just a dummy variable, right? I can write it as anything, so I'm just gonna write it as tau. And you see, we now see that these two are exactly the same. Okay, these two are exactly the same. This one is b, right? This one is b, and a is equal to b now. So a is equal to b. So the system is time invariant. All right. The last one probably for today is going to show this. Now I'm going to show that this one is not time invariant. Now the trick is to see this. Look at this one. If I'm messing with t here inside of the parentheses, then I suspect that the system is not time invariant. Okay, I have 2t here, right? If I scale the signal, then it is not time invariant. Okay, so again, as usual, I'm gonna draw this. I'm gonna draw this diagram again. Oops, sorry. Oh, yeah. Okay, now I'm gonna erase this, and I'm gonna erase this, and I'm gonna erase this. Now the way we define the system is whatever the input is, it will condense the input, right? It will make the input thinner, 2 times thinner. So whatever x is here, I have x of 2t here. And then I delay, so I have to plug in t minus t0 instead of t, right? So I'm gonna have x of 2t minus t0 here, and that is equal to x of 2t minus 2t0. Now let's look at the lower path. I have x here, right? I delayed by t0. I have this one. So what the system does here is that it will plug in t as 2t. So what it does here is we have x of 2t minus t0. Remember, it will shrink the signal twice, 2 times. So whatever we have t here, okay, where there is t, I write it as 2t. That's it. All right. So you see at a is so when t0 is not equal to 0, a is not equal to b. So that means that it is not time invariant. Okay, that's what the system does, right? That's what the system does. All right. Yeah, I think we should end it today. We don't have enough time. And next time, see you again next time, same at WebEx at 10:30. I am recording this, and I'm gonna put it up to YouTube, and then I'll give you a link to check it out later. And as for now, you have any more questions, please?
Do we have a checking attendance?
Oh yeah, we do. Let's see today. Borel. Here. Write down Borel. Borel is a mathematician. Borel. You can look it up the web. Borel. Search Borel, and then a lot of things will come up. All right, so see you again on Thursday. Bye bye.
Bye bye, ครับ
bye ครับ